So how did your test go, Rob? It was very quiet last time
Oh,
and you were not here.
I know. I kept wanting to answer questions during the lecture when you would ask and be like, oh, that's recorded. It's not going to do anything. Everything's normal so far. So they're probably going to send me to an electrophysiologist.
Electrophysiologist.
Or they may decide that since I maintained target heart rate for the duration of the stress test that I was supposed to, and it didn't spike, that maybe the medication is all I needed. Because apparently Chris Mandrell told a story about having the procedure that they would have me do if they were going to correct it.
Who's this?
Chris Mandrell.
Oh, here. Oh,
Yeah, he had it, and he described the procedure, and it's like, that doesn't sound fun. I would like to avoid that at all costs.
When did he have?
I'm not sure. He was just telling the story in class. And it was one of those stories that did not make me want to jump up and go have that procedure done.
So there is a homework that is optional. You don't have to submit. And the final exam, since I'm so slow, what I did was I did post it. So there are there'll be 5 questions in the exam. 3 and 4, I have posted it. Sorry, 4 and 5, I have posted it. 3 will be posted probably in 24 hours, hopefully. And 1 and 2 will be in class. Relatively simple. Just go over all your homework and it will be a small piece out of the homework. Something that was very straightforward. You've seen this in the midterm 2 that we did. I'll make it extremely straightforward. Try to get reasonable. So homework 11. At this time, due date doesn't really matter. It's optional. Final exam. Preview posted. Problem 3 will be updated. And problem 1 and 2 in class. And it's due on May 6th, Friday. And anybody else? Okay. So it's the last lecture. This pretty much will take care also of problem 4 in your exam. This is very similar, but I'll be a little, I'll use a shortcut here. Everything happens in a straight line, so I won't even bother to talk about the rest of the components. In your exam, you really worry about those components, and it's pretty straightforward. It's almost trivial extension there. So that's just for simplicity. That's what I'll do. So Let's go back. We were doing relativistic kinematics, and today we want to do dynamics. It's like going back to Newtonian physics. First, you do not introduce force. You introduce position or displacement, velocity, and acceleration, and you pretend that there is a force and there is a motion going on. You work with that. That's what we have introduced as of now. And there is a class of problems you can work with that. Very nice problems, but we won't have time because of the way I arranged this. So we are having limited time. So we now go and introduce the idea of force. And when we, or we have already introduced the idea of acceleration. When we introduce the idea of force, we have to talk about relativistic force. So remember in Newtonian physics, when you start these problems, you introduce forces like the normal force, the gravitational force, mg, the force of tension, force of friction. These are the forces you introduce. They were all empirical ideas of forces. That's all good. Here we want to have a relativistic force. We have to have a concept of a force which is by construction relativistic, and it is not easy usually, but we are lucky here in the sense that electromagnetism from the start, even before Einstein, is relativistic. Everything in electrodynamics that you do is relativistic by construction, if you want. So whatever happens in electrodynamics is already relativistic. So Lorentz force, that Q times electric field, and QV cross B is ready-made for us. That is going to be our definition of force. So whenever you think of relativistic dynamics, you want to keep the idea that electromagnetism is relativistic already there. So we will talk about a charge moving in a magnetic field, charge moving in an electric field. Those are the classic examples we will do uniform cases. And when the initial velocity is not in the direction of the electric field, that's your final exam problem. Okay, right? Roughly motivated. So let's go back and remember. So this is now relativistic dynamics, if you want. So we have introduced the idea that what is it? C et over ds, correct, is equal to gamma. This is coming from the fact that minus ds square is equal to minus c square dt square plus dx divided with dx. This can be rewritten in that form for our convenience. And the fourth position x mu is equal to c times t and the vector x. For velocity is u times alpha. This can be alpha x mu, it's alpha. That's c times c times gamma and b times gamma. Then we did for momentum. P alpha is equal to mu alpha. That's equal to mc gamma mv gamma. We pretty much, this is a postulate, or this is where you connect with physics. You said that P0, which is mc gamma, is equal to energy over c, or energy is c, mc square times gamma, and the relativistic momentum, or the just momentum itself is mb gamma. So these two are inbuilt. He then introduced the idea for acceleration. And that was A alpha. And that will be, you don't have to really write the explicit form. That's the derivative of this. So this will sort of be gamma times times derivative of C times gamma B. So acceleration has this feature that d gamma, the derivative of the there's a word for gamma. What do you call gamma? It's like, check out what gamma. There's a word they use for some factor. Maybe Lorentz factor. Yeah. Scale factor. But what is it called? A name. I don't remember. So what we did last time was that we explicitly evaluated this, and that's convenient, but often it is good to keep it as it is, and that will become your equations of motions also in a sense. And it was convenient to realize that d gamma over dt is equal to what is this? A dotted with v, and there is a 1 over time on the left hand side. So there are two velocities on the right side. So this is c squared, and is that what it was? Or was there a gamma in it? I think gamma cubed. Yeah. Minus, no, multiply. Multiply by gamma squared. Everyone like this?
Gamma cube. Nice one.
Yeah, I thought it was gamma cube from my memory. So I think it's gamma cube. Let's quickly do this. Confusion. And we use the fact that A alpha times, so we used A alpha times U alpha is equal to 0. So multiply these two quantities. So this becomes C times gamma squared. So when I multiply this plus this, there's a C squared. C gamma squared and d gamma over dt. That's the time component, which comes with a negative sign, plus v times gamma, and then there is a gamma squared, d by dt of v gamma is equal to 0. Derivative of velocity is acceleration, but this leads to two terms. So, and there is a dot product here. So this is minus c squared, gamma squared, d gamma dt, plus v dotted with acceleration. V dotted with acceleration, and that is a gamma cube, then gamma and gamma plus. If I have v squared, gamma squared, gamma over dt is equal to 0. Take this common c square gamma square d gamma over dt, and so let's say minus, that's equal to 1 minus v square over c square. And that's equal, and then that's on the right hand side. When I take it to the right side, I can write this as v dot a times gamma q. But 1 minus v square c square is exactly 1 over gamma square. So this cancels out. So d gamma by dt is v dot a. So yeah, so this is gamma q. So this, so this is correct. So that matches that. Okay. So that's takes care of the acceleration. Now we introduce force. As I said before, force is on the left hand side. Force will be anything coming from electromagnetism. So the Newton Einstein or generalization of Newton's law in the 4 vector notation is F alpha is equal to m a alpha. That's it. Here it is a little, at this point it might seem incomplete, because what is F alpha? I haven't introduced F alpha. F alpha is anything that is relativistic. So you have to go to electromagnetism for that. But at this stage, let's do the following. What we will do is we will compare this and this quantity in here. That's what we will use for equations of motion. What one can do is that start from electromagnetism, have electric and magnetic field. We want to find the 4 vector generalizations of that. It is not a vector. Electric field is not a vector under Lorentz transformations. It's a part of a tensor. Is that a familiar idea? No. So let me quickly, I think that's important. Right. So crash course in a sense. So we have done acceleration velocities. It is good to know that in Maxwell's equations, we have current J, that is rho, right? Charge density, current density. What else shows up? That is electric potential. That is magnetic vector potential. What else can you think of in electric electricity and magnetism? And that is electric field and magnetic field. As I've written it, these are actually the 4 vector generalizations that comes up. So for current is, oh no, vector needed now, right? So J alpha is equal to C times rho times J. So charge density is the 4th component of current density. A alpha, that's a 4 potential now. Is 5 over C times A. And why I brought in here is that now electric and magnetic field, this is not convenient, right? The vector and the scalar you put together, and it seems like that's a decent thing, but these are 2 vectors now. How do you put 2 vectors to construct a 4 vector? It's not a 4 vector at all. It is actually a tensor now. But how do you construct a tensor out of 2 vectors? I'm not saying that this is the way to do it. It's just that this is how it comes out. It makes sense. It doesn't mean that anytime you have two vectors, you can construct a 4 vector out of it. It has to be part of the equation. So this is called the electromagnetic field tensor. So this is F alpha beta. This is electromagnetic field tensor. Having said this, I should say there is nothing new in this. Physics-wise, nothing changes. Like all this doesn't change the physics except for these two pieces. That's the only new thing. And similarly, electromagnetism stays the same. It's just that it's a convenient way. You can write your Maxwell's equation on your t-shirt. That's some advantage. But what is F alpha beta? This is equal to 0, to antisymmetric. So that's electric field, first component of the electric field, and that is L divided by C. E2 over C, E3 over C. It is antisymmetric. So this is 0, 0, 0. And this is B3 minus B2. B1. It's antisymmetric. I can fill this in now. This is B2 minus B3. This is minus E1 over C minus E2 over C. While I'm doing this, it is convenient to have one thing in your mind. We should always look for in Lorentz or Einsteinian relativity, the basic idea is what remains the same. We don't care for position and time. You never measure position and compare, right? It's the x mu, the distance. How do you say that? The length of this vector, the 4 length of this vector that matters. 4 length of this is speed of light. So those are the quantities that doesn't change. Electric and magnetic field has this interesting feature that you have a charge. If it is at rest, that means I'm sitting on the charge. What is its magnetic field? So magnetic field due to a point charge, when the observer is sitting on the charge, what is its magnetic field? It's 0 because its velocity is 0, right? If you're not moving, current is 0 in that frame. So if the current is 0, magnetic field, there is no source for the magnetic field. Is that a clear idea? Right? If a charge is at rest in the frame, it doesn't create a magnetic field. But now you jump out of that frame, the charge is still there. But now you start moving backward. Right? You're not doing anything to the charge. You start moving backward. What happens? You will measure a magnetic field. Right? So magnetic field is not an invariant quantity at all. So in one frame magnetic field, second frame magnetic field, they don't match. In fact, in one frame it will be 0. That's the extreme version. But in one frame you say there is no concept of a magnetic field in another frame. So then the question comes, what should we compare? Right? It will be good if we can compare the two quantities, and there is a tensor here. But what is the invariant structure of that? Whenever you have a matrix, remember eigenvalues play an important role. This is a Lorentz transformation we are talking about. Eigenvalues remain the same under similarity transformations. But one can show that all the similarity transformations are consistent with Lorentz transformation. I'm not going to show that here. So then the question comes, what are these eigenvalues built out of? That is what is going to remain the same. So that's what so invariant, instead of talking about invariant quantity, which you can say square of this will be invariant. That's another way of it. So what is invariant is? It is E square minus B square. And since I need the dimensions, this remains constant. It's invariant. It's frame independent. Another quantity is E dotted with B. Immediately, you come up with three different situations. One is if E is greater than C times B, this is purely electric. So this means that there exists a frame, there exists a frame where B is equal to 0. So there exists a rest frame where I can set that equal to 0, right? Pure magnetic field. If E is less than C times B, there exists a frame. We can exists a frame where E can be chosen to be equal to 0. And there is one more. E is equal to C times B. Where do you see electric field magnitude to be exactly equal to C times magnetic field? Both electric and magnetic field magnitudes are the same of 2s field. Yes.
Electromagnetic wave.
Electromagnetic wave. That's an electromagnetic wave. EM wave. So the three things that we study in electromagnetism, one is pure electrostatics, if you want. This is electrostatics, this is magnetostatics, and this is electromagnetic wave. That can be always, even though you're not in such a frame, go to a frame and then make it electrostatic. You can convert every problem into electrostatic or magnetostatic, and there's a third one, this is EM, electromagnetic. The force here is F is equal to Q times electric field plus Q V cross T. That's your force, and this is relativistic by construction. But this is the three components. What is the fourth component of force? For that, it is good to see it in this context. You can also say acceleration, right? Or think of, let's go back here now. Okay. Changing gears here. I'll combine the two in a second. So let's go back to force F. On the left hand side, let's say this is derivative dp alpha over ds. So that's the way of writing, right? Instead of saying, typically in Newton would have, Newton wrote this as rate of change of momentum with time, but now this is rate of change of for momentum with respect to a proper distance, and again for dimensional reason I can put a C. Convert this to C dt over ds is times dp alpha over dt is equal to m a alpha. That's your gamma here. So gamma times d by dt of p alpha. P alpha, first let me write it in this form. That's E over C and P, right? That's my left hand side. On the right hand side, let me write here. Right? This is M times, so I'll write this as gamma times d by dt of mc gamma times mv. It is true. Notice, even though the way I'm writing it, seems to be suggesting that I'm working with the force, I'm still working on the left-hand side of the force. It is a rate of change of momentum I'm talking about. I'm not taking any force and working with it. Right? For that, I have to go here. And I'll do that in a minute. We will say that we're doing electromagnetism, and at that time I will invoke it. But here, it is good to see this is dp by dt. That's your force. What's the fourth component of force as a physical quantity in introductory physics? What's the fourth component of force? Fourth component of momentum was energy. What's the fourth component of the force?
Power.
Power, right? Because this is rate of change of energy over time. Energy over time is power in Newtonian physics, right? And so gamma you can cancel. So for our purposes, we will have, if you want, dE by dt 1 over c is equal to d by dt of mc gamma. These two are the same idea. And now I have to say what this is. So I have to give an expression for power, and this will be power. I have to introduce that from electromagnetism. In electromagnetism, power is equal to, let me write that actually. What is power equal to in electromagnetism? A convenient way you can think of that, dE by dt is also F dotted with V. Is that familiar? Energy over time is equal to F dotted with V. Is that a familiar idea? Like somewhere in introductory physics, you can see this as energy is force times distance, and then you will do F dotted with V. Yeah, quiz. Okay, let me not do it here. But show that dE by dt is equal to F dotted with V. How do you submit your quiz at this point? Okay, this is not you don't have to submit, right? This is optional quiz. Okay, so you don't have to submit the quiz because we don't meet after this, so you cannot submit. You don't have to submit in my mailbox. So this is equal to, actually there is a small challenge here. I have E over C. Yeah, I can say I'll put the C on the right side. That's convenient. And then I will say this, then it is power, right? So it's F dotted with V. When F is the electromagnetic Lorentz force, now I have introduced the force. These two are pretty much the same definitions. I have written it in different form. E is mc squared. Gamma, I have just written it in one form or the other. And the second expression there is equal to dp by dt is equal to, if you want, mv gamma is equal to force itself. So summary, right? So I went through this quickly, did not discuss it too much. Summary is that your Newton's law in relativity is the following equations. First, define your energy as mc square gamma. Have momentum defined as mv gamma. Those are the definitions. And the Newton's law is derivative of energy with respect to time is equal to F dotted with V, and derivative of momentum with time, which is, these are the definition, right? I wrote it twice there. That's equal to F. And here F by, we are saying F is Q times electric field plus Q V cross B. So that's your in Newton's, when we do Newtonian physics, we just work with this. Right? We do introduce this, we rarely use this in the introductory level because it just stays in a remote corner. Any questions at this stage? That's my building block here, and we will use this now for, I'll do at least one problem. Well, I'll do the magnetic field problem, motion in a magnetic field. And if I'll try to attempt on an electric field, but if time doesn't allow, that's part of your final exam. Any comments? Oh, I mentioned what's the power and in electromagnetism, it is F dotted with V. So you can multiply with Q times V dotted with E. What is V dotted with V cross B? 0. So magnetic field doesn't create power, right? You don't lose energy in a magnetic field. But Q times V times electric field is, remember, Q times V times electric field is equal to Q times V is the current due to a point charge. So if you're talking about current density, so this is per unit volume, let's say, is J dotted with E. If you have a current, there is a good chance. So basically, you're using the energy from the electric field to move the charges. That's the basic idea. There's a transfer of energy from electromagnetic to mechanical power. So that's where the transfer happens. Okay. Say motion or charge, electric charge, understood? Charge in a uniform magnetic field. Our equations are E is equal to M of the magnetic field, right? Uniform magnetic field. So let's say B is equal to B times Z hat. It's not really necessary to choose this. If it was Newtonian physics, how would you go about doing this? Let's really quickly do that. So in Newtonian, now you're doing Newtonian. You would say dP by dt, so d by dt of V actually, V is equal to mass times that, mass times acceleration is Q V cross B. That's what you would do. It's B is uniform, constant, even direction wise it's constant. So you would say dP by dt is equal to V V crossed with, this is a constant, so I'll write that as omega. So this is omega C. Why that C? What does C stand for? Why C? Cyclotron, very good. This is called the cyclotron frequency. If there was no vector, I just introduced a vector associated with cyclotron frequency. So that's omega c. So, so that's good. And you can do one thing. We can actually multiply V dotted with this quantity. That's equal to 0. Because cross product and dot product doesn't get along. But this immediately implies that we have d by dt of half of mv square, v dotted with v, and multiply by mv, let's say now, is equal to 0. Which implies that half mv square is a constant. So kinetic energy is a constant. So half implies half mv square is equal to a constant. And yeah, so let's have this. Let's not go beyond this. We can actually go and show that this is what's the curve of a particle that goes in a magnetic field. It goes in a circle, right? And one would like to know what is this curve in relativistic physics? Right? Is it really circle or not? But what we will here do is that what is the cyclotron frequency? Cyclotron frequency is the period with which it goes, and what do you expect would happen? What will happen to omega? Look for the dimensions. Frequency is 1 over time, right? And time transforms in a certain way in relativity, right? So time gets dilated. So you expect that 1 over frequency, cyclotron frequency, will get dilated. That's what you should get. Right? So let's see if we can motivate that part here. So, so now let's do relativistic. We can again somewhere else we can do this in detail and show that it's an equation of curve. But in the limited time, let's say let's just do this the cyclotron frequency, relativistic. So relativistic part now is dp by dt. So we have gamma, right? So d e by dt. So d by dt of mc gamma is no mc squared. This is square gamma is equal to f dotted with v, which is q v cross b dotted with velocity. That's equal to 0. So gamma doesn't change. Gamma, remember, is 1 over 1 minus v squared. This doesn't change, this remains fixed. So what happens to velocity? So if gamma has to remain the same, what will happen to at least velocity squared? And that has to remain the same. Same idea, right? Kinetic energy still remains, for kinetic energy, the Newtonian kinetic energy remains the same. There it is, mv gamma. That changes. So velocity will change, but the velocity square is not going to change. So that's one relation we have. We'll come to that and do this, explore this. The second is our MV gamma, right? MV gamma, that's equal to Q times V cross the T. Let me write this as, this is 0, MC squared is anyway constant, so this implies that gamma is, or the change in gamma is equal to 0. And we also have, I will move this omega out here, so we have d by dt of V times gamma is equal to V crossed with omega. When I take this derivative, I have to find the change with velocity, and I have to find the change with gamma. But I just now convinced you guys, hopefully, that gamma doesn't change. So that means this can come out of the quantity. So what I have is that, so this together implies that dV by dt is equal to V crossed with omega c over gamma. If you want, this is omega c prime, where omega c prime is equal to omega c over gamma. And from this point on, you don't need to do anything. Most of Newton's laws remain the same. So is the trajectory in relativistic physics in a uniform magnetic field going to be a circle or not? It will be circular because it's the same equations. What will change is its frequency. How many times it goes around the circle will seem different to you, and it will be dilated, or in this case, it will be frequency is contracted, time is dilated. That's all. So magnetic field is the easiest generalization to make when you go to relativistic physics, because the motion is governed by the same equations. Only one transcription you need, and that is that the frequency, the cyclotron frequency, is now having a factor of Lorentz factor. This is for the Lorentz factor. That's what it's called. So there's a Lorentz factor that comes in. Yes, one of the quizzes. Yeah. So this is Lorentz factor. Okay, so now you know magnetic field. So now let's do electric field, right? So again, notice the basic idea is that energy and momentum changes, and you have to do F dotted with V and F, and then work with the equations. Clear? Okay. Well, let's do charge in an electric field next. In a uniform electric field. So our equations will be same as here, right? So now electric field for our, I think in your exam that I prepared this in the morning today, is I choose this in the X direction. So as you notice in this case, it was not really necessary, at least in this case, it was not necessary. There we will, everything will happen in the same direction. Matter. Okay, so now we are directly do relativistic electric field, and in Newtonian physics is straightforward, right? So what's the equations? X is equal to, so acceleration. So Newtonian is very straightforward. You would say dA, right? So this is dV by dt times m is equal to Q times electric field. So, and this is, let me define Q times E over M as a constant. That's your E naught. That remains the same, right? Electric field is a constant. Q over M, instead of carrying that quantity all through, A naught is a measure of my electric field. So my equations is dV by dt times a constant. That's kinematics, right? So velocity is equal to A naught times t plus a constant, which is initial velocity. Integrated again, I'll get x minus x naught is equal to v naught t plus half acceleration squared. Should do this correct? I think so. Okay, so relativistic. Our equations now are d by dt of mc square gamma, right? Energy, right? Change in energy is F dotted with V. So this is Q E dotted with velocity. And the second equation is d by dt of mv gamma is equal to Q times E. Rewrite in terms of this A naught. So then we have, so this is d gamma over dt. Divide out by mc square. M is already A dotted with V. So that's A dotted with V over C squared. Let me do one more. Picture V over C is beta. So that's beta. Is that visible there? Yeah, that's beta. And that is A over C, or A naught over C. A naught over C has the dimensions of 1 over time. 1 over time is like frequency. Let's call this omega naught. It's not cyclotron frequency. It's just a scale in time. So that's omega naught. So that's one. Like that's just getting rid of all the dimensions and getting the parameters straightened. Do the same thing here, and this becomes d by dt of V. Instead of V, let me write this as beta times gamma. That's equal to QE over an acceleration over C. So that's omega naught. That's your two equations, if you want. keeping time factor as a limitation here, I'll say I'll stick to initial condition. This is what I say. It's slightly different from your homework there. You have trivial generalization, you do that. And this is that you're saying that initial velocity v is equal to 0. So v at time t equal to 0 is equal to 0 as a vector. So you start from rest. Start from rest. If you start from rest and you exert an electric field, charge will move in the direction of the electric field. Everything is happening along that line. I don't have to worry about other directions. So x is the only quantity in here. All these vectors can be dropped. So in that case, for simplicity, it is okay to d gamma over dt is equal to a constant omega naught times beta. Beta, remember, is the velocity. And the second equation is d by dt beta times gamma is equal to a constant omega naught. The first one is a little more involved because gamma has a velocity beta inside in it, right? So it's a derivative of that is equal to this. But this one is straightforward. This is a constant. I know how to integrate this. This immediately tells me that beta times gamma is equal to omega naught t, right? That's my integration plus a constant. Plus a constant. But at t equal to 0, I've chosen my charge to be at rest. This is equal to 0. Because it is at rest at t equal to 0. That gives me an equation for beta now. So square this. So this is beta squared over 1 minus beta squared is equal to omega squared t squared. Which implies that beta is equal to, so there is a minus that becomes a plus, and so that I think is omega naught t over, so it was a minus, it becomes a plus, so it's plus omega squared t squared.
The last,
This one, I just squared it. So I just squared this beta squared, gamma squared, is omega squared, t squared, gamma squared is 1 minus. Hurrying a little, but that's because it's the last lecture. It will allow me, but we are almost there. So beta is 1 over c. So v, right? So velocity. So v is v as a function of time is equal to omega naught times ct over 1 plus omega squared t squared. That's nothing but dx by dt. I'm interested in x as a function of time, so integrate this. So x would be equal to integral of, so c that out, so c times dt omega naught times t over 1 plus omega squared t squared. Let me put an omega naught in front, divide by omega naught. And then I can substitute 1 plus omega squared t squared is equal to s squared. And then I have 2 times omega naught squared t dt is equal to 2s ds. Yeah, so omega squared t dt is 2s ds, right? So this is equal to c over omega naught is nothing but c over omega naught. What is it? C, nothing. C over omega naught. So this is s ds over s. What happened? S cancelled out. Is this correct? Yeah, no, okay, so this is equal to c over omega naught times s, I guess, right? Plus a constant if I want. So plus a constant. So x is equal to c over omega naught. S is nothing but 1 plus omega squared t squared and plus a constant. We put a condition that it goes through x equal to x naught. So initial condition at t equal to 0, let x be equal to x naught. Then I have this implies that x naught is equal to c over omega naught plus a constant. So the constant is x naught minus c over omega naught. So we have our equations as x minus x naught is equal to c over omega naught times 1 plus omega squared t squared. Constant is x naught minus c omega, so this is minus 1. To see the fact that how this look like, let's actually change this a little bit. Put this on to the left. So I have x minus x naught. So that is minus becomes plus. So that's c over omega naught. And then square this. It's equal to c over omega naught, c square over omega naught. 1 minus 1 plus omega square square. That is omega squared cancels out. So what I have here is x minus x naught plus c over naught square minus c squared t squared is equal to c squared over square. That's an equation of a hyperbola. If this was a plus, that's an equation of a circle. Right? X squared plus y squared is equal to a constant in time, if you want. But now this is a minus, so this is a hyperbola. It's also good to realize that a naught is equal to c times omega naught. So that means whatever the c over omega naught actually, this quantity here which has the dimensions of distance is c over omega naught. Omega naught is a naught, so this is c squared over naught. This is a hyperbola. If this was x and that's your t, that's how it looks like. And this point here is x naught. Oops, I didn't move it. Three more minutes. It's good to see how this works. In what sense is this a generalization? How does the limiting case goes? In some limit, this should be Newtonian, right? So let's say how this looks like. This is the curve we have. That's the speed of light, and it starts from here, and that's your parabola there. As a parallel line, I have, this is a parallel line to that speed of light curve. Whenever the slope goes more than that line, that means I'm going faster than speed of light. If it was a parabola instead of this will look like this. And it crosses, right? Not only crosses the speed of light, it starts going faster than speed of light right here somewhere. And the slope goes more than that. So this is parabola. Parabola. And that's hyperbola. So it seems like when you have this x and t, if you fix your time to be very small, if you limit your times to be very small, where the acceleration has not really started moving or changing the velocity too much, you should get Newtonian physics. Correct. So for small times, it should work. So let's try to ask, so t is very much less, right? But less than what? Like that has to be a scale, but we do have a scale in time, and that's omega naught. Right, so let's say t is very much small compared to omega naught, which means omega naught t is very much less than 1. That's a natural scale. So we come back here and do that. X minus x naught is equal to c over omega naught times 1 plus omega squared t squared. That's your exact result, minus 1. That's your hyperbola. But now make an approximation. For small omega naught t's, I can expand this. So it's 1 plus half omega squared t squared. And there are higher terms, and then there is a minus 1. Great. This is equal to one cancels out. So I have 1 by 2, and there is 1 by 2 omega naught times c times t squared plus higher order terms. But I had defined c times omega naught to be an acceleration, right? So that is my acceleration. That's constant acceleration. In fact, that's a proper acceleration also in this case. So it does use the right limit, and you will in your, this is part of your final exam also, homework for final exam also, and you will generalize this to when you have an initial velocity. I'll stop with this. Even the last lecture I took 2 minutes extra. Thanks for listening all through the semester. Good luck with the final exam. That's all. Good luck.
here next week if you have any questions.
Yes, yeah. If by any chance I'm not in the department itself, if you can send me an email saying that you plan to come, I'll come.